friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello yes, today I'm going to show dynamic analysis or transient analysis of a beam using ANSYS mechanical APDL. Let us see the statement of the problem. The problem states that a vertical beam of length 1 meter and cross section 1 centimeter by 1 centimeter is fixed at both the ends, and an impulsive force of 100 kN is applied at the center for a duration of 0.01 second. Perform a transient or dynamic analysis of the system and show the displacement of the middle node for a duration of 0.1 second using the following data. The material specification is provided as modulus of elasticity is 2 into 10 to the 11 Newton per meter square. Then Poisson's ratio is 0.3 and density equal to 7800 kg per meter cube. Let us understand the problem. For understanding this one, we need to draw it. Alright. Let us make a sketch for understanding this one. This is a beam which is fixed at both the ends, top end and bottom end, and which is having total length of 1 meter. Right. This is fixed at top and bottom, and at the middle we have to apply a load of 100 kN at this location. This will be the load that to be applied. The load will be a step load. It will be applied for a small duration of time, 0.01 second. After that, the load will be removed, and then it will continue up to 0.1 second, and up to 0.1 second we need to show the deflection of the middle point using ANSYS mechanical APDL. Let us understand the problem again. The beam is having total length of 1 meter and it is fixed at both the ends from top and bottom. At the middle we have to apply a load of 100 kN, and the load will be applied as a step load. It will be applied for a duration of 0.01 second, then it will be removed, then it will be continuing up to 0.1 second, and within this time we need to find out the displacement of the mid node using ANSYS mechanical APDL. Right. So without wasting time, let us start our analysis. Let us close it. First of all, we need to create a directory, and in that directory we need to save everything. After that, we need to change the title of this analysis. Let us change the title as FEA 7. Now to see the title, we can click plot replot. It will be visible at the lower left corner. Next to that, we need to start from preferences. It is a structural analysis, so structural analysis checked in. Okay. Next to that, we need to define elemental properties, and it will come from preprocessor. Element type, add, edit, delete. Let us add that element. We are providing beam 3D finite strain. Okay. Let us close it. Next to that, we need to provide material properties, and it will come from material models. Structural, linear, elastic and isotropic. Isotropic means material property remains same in all directions, right? And modulus of elasticity is given 2 into 10 to the 11 Newton per meter square. So it will be 2E11, and Poisson's ratio is 0.3. Okay, done. And density, it will be 7800 kg per meter cube, 7800 kg per meter cube. Okay, done. Let us close it. Next to that, we need to provide sections. The beam is having a square cross section of 1 centimeter by 1 centimeter. If you convert this one, it will be 0.01 meter by 0.01 meter, right? So it will be a square cross section. Beam, common sections, and let us provide breadth of this one is equal to 0.01 meter and height also 0.01 meter. Okay, done. Next to that, we need to start modeling. For modeling, we can create nodes or we can create key points also. Let us create key points in active coordinate system. Another thing is, it is a vertical beam with a span of 1 meter length. So what we'll do is, the first location of the node will be at a distance of 0.5 meter, up, and the next one will be 0.5 meter down. So it will be in the y direction, so it will be 0.5 apply, and second one will be minus 0.5. Okay, so two nodes we have created. First one is 0.5 meter and down is also minus 0.5 meter. Total length is equal to 1 meter. Alright, done. Next to that we need to create lines. It will be a straight line and we can join these two key points to create the line. Done. Okay. Next to that we need to mesh it. So starting with mesh, size controls, manual size and lines. Let us select the line. Okay, and numbers of elemental divisions, we are considering this one to be made up of 10 elements, so it will be having total 11 numbers of nodes, right? We are considering numbers of elements to be 10. Okay, so it is divided into 10 numbers of elements. Now we need to mesh it. Mesh, lines, pick all, meshing is done. Right? Okay. Next to that we need to apply boundary conditions from here. Analysis type, new analysis, it is a transient analysis. Right? And we are following full method. Okay, done. Solution controls. So from basic you can select that time at the end of load step equal to 0.01 and we are considering time step size as 1. And from the transient setup we can include frequency response and also amplitude decay can be taken up. So okay, next to that we need to define loads. Apply structural displacement on nodes. Right, to view the nodes what can we do is we can plot the nodes from plot here, plot nodes, so nodes will be visible. We can select these two extreme end nodes. Okay, and these two should be fixed, so select all degrees of freedom and the displacement value is 0. So these two, the top and bottom point is fixed, and at the middle point next to that we need to apply some load. Right, now the thing is, in this case we'll be doing something else, not like the normal one. We have applied one boundary condition, then we can go to load step options and from here we need to write ls file. Let us consider this file as ls file 1, and again in the next step we need to see the selection controls. We will run this one for next another 0.01 second, so it will be 0.02 second, and time increment and time size everything will be equal. Okay, now define loads. Apply structural force moment on nodes. Select the middle node, apply along x direction, it will be 100 kilonewton. Okay, load is applied. Then load step options, we can write this one as ls file number 2. Let us remember what we have done. In first 0.1 second we have applied the boundary condition, that is the top and bottom point is fixed, and during that time we didn't apply any kind of load. And in the next 0.1 second we applied a load of 100 kilonewton at the middle point. In the next step what we'll do is we will remove that load. So again, analysis type, solution controls, and in the next step 0.3 seconds we'll remove that force. So define loads, delete structural force moment on nodes. Let us delete that force from the middle point. Deleted. Now again, as per normal practice, we need to see the load step options and we can write the ls file as step number 3. Done. We need to repeat this one again for several times. Solution controls to run for the next 0.01 second. that is 0.04. Okay, and in this case we are not applying any kind of load because in the previous step load was removed. Now it will go as continuously up to 10 steps, right? So load step options, write ls file, and step file number is 4. Okay, done. Again, analysis types, solution controls, this one will be 0.5, and okay, similarly load step options, write ls file, it will be number 5. Okay, the same way we need to continue up to 10 steps, right? Again, analysis options, solution controls. In this case we are not applying any kind of load was removed. Now same repetition is going on. 6. Okay, load step options, write ls file, it will be number 6. Okay, again analysis type, solution controls, it will be 0.07. Okay, and load step options, write ls file, it is 7. Okay, again analysis type, solution control options, time at the end of load step equal to 0.08. Okay, load step options, write ls file, and that ls file number is 8. Okay, again analysis type, solution control options, time at the end of load step equal to 0.09. Okay, and load step options, write ls file, and this file will be file number 9. Okay, and the last one, analysis type, solution controls, it will be 0.1. Okay, and load step options, write ls file, it will be number 10. So you can remember what we have done. In the first step we have applied the boundary condition, that is fixed the top and bottom load. During that time we didn't apply any kind of load. In the next step we have applied a load of 100 kilonewton at the middle of this beam, and the next step we removed the load, and this way we continued up to 10 steps, right? Now we can solve it. Now while solving these things, generally we need to solve from current ls, but here we need to consider those ls files for solving these things. So from ls file we have made already 10 files. It will be starting from number 1 and ending file number will be 10, and it is increasing by number 1. Okay, let us run this one. So solution is done. Now we can see our results. As it is a transient analysis, at different times it will be having different solutions, right? So first of all we'll see the result from time history post processing, then you can see results from general post processing. First of all, time history post processing, and first of all we need to load the data from here, and we want to see, do you have solution degree of freedom solution of x component displacement? Because the beam was vertical, we have applied a load in the x direction, so we want to have displacement in x direction, and the variable name is ux2. Okay, now let us select that location, that is from which we want to see the response analysis. We want to see the response analysis of this middle node. Selected. Okay, it is done. Now we can see the response of this one through listing files. You can see it from here, list data. These are the responses, right? These are the different times you can see different responses for the last result actually, right? Okay, now what we'll do is we can see the results from graph that can be viewed from graph data. Let us see this one. This is the graph. So this is the origin. You can see this is actually one sinusoidal curve, and ultimately it will be diminishing. It is a damped vibration. Initially we didn't apply any kind of load. After some time we applied a load for a small duration of time, then we removed the load, then it was vibrating. It was a damped vibration, right? In this transient analysis we have performed 10 different sets of analysis, and for each set at different times we can see the responses of different nodes that can be viewed from this general post processing, right? So we can read results from here itself. Read results, first set, and that can be plotted here itself from plot results, contour plot, nodal solution, and when you see degree of freedom solution, it will be x component of displacement. Okay, see, first case when time was 0, during that time the beam was like that, it was a straight beam, right? In this case we are having a lot of nodes, as we divided this one into some specific numbers, so all the nodes were having 0 displacement, and that can be viewed from the listing file also, right? You can see list results, nodal solution, dual solution, x component of displacement. Okay, you can see the displacement of all the nodes. We are having total 11 nodes here, right? As I told that we have made this one into 10 elements, and in between 10 elements total 11 nodes are there, so each node is having 0 displacement in this case, right? We can save this one as step 1, save as 1. We'll save this on the desktop 1, close it. Again we'll see the next results, so read results, next set, plot results, nodal solution, x component of displacement. See, next set it is varying, the top and bottom node is fixed, but the other nodes are actually displaced at little distance away. So this is the displacement for the second step. Now we can see the displacement in the terms of like listing also. So list results, the same thing you can view in the form of list results, nodal solution, x component of displacement. This is the displacement of second step after 0.02 seconds, right? Okay, now we can save this one again, file, save as 2, done. This way we have to save all these things, right? All the different set of results, we need to save it. Again, read results, next set, plot results, nodal solution, x component of displacement. This will be a little bit of different compared to the previous one, but through our eyes it cannot be viewed properly, but that can be seen from list results in a better way. So nodal solution, x component of displacement. Okay, you can see load step number 3. We can save it as file number 3, done. Again, read results, next set, plot results, contour plot, nodal solution, x component of displacement. This is plot number 4. This is step 4. We can save it. So we're going to see the list results of this one, nodal solution, x component of displacement. This is load step 4. We can save it as number 4. Now this is having some meaning. Why we are saving? This one will be cleared after some time. We need to save all the 10 results, right? Again, read results, next set, plot results, nodal solution, x component of displacement. This is a little different. All sets are actually different. Through our eyes it cannot be viewed properly, but when it will be vibrating, that one will be easily visible, right? Okay, now again we need to see the results in the form of listing, list results, nodal solution, x component of displacement. This is step number 5, so we can save it as file number 5, done. Again, read results, next set, plot results, nodal solution, dual solution, and x component of displacement. This is the displacement. Now we can see it again from listing results. So nodal solution, x component of displacement. This is the result of load step number 6, file, save as 6. Okay, close it. Next one is results, next set, plot results, nodal solution, x component of displacement, done. Again we're going to see the same thing with listing results. So nodal solution, x component of displacement, it is load step number 7, so we can save it as file number 7, done. Close it. Read results, next set, plot results, nodal solution, x component of displacement. Now we want to see the same thing in the form of listing, list results, nodal solution X component of displacement. This is load step number 8. We can save it as file number 8. Okay, close it. Again, read results. Next set, plot results. Nodal solution X component of displacement. This is the result. We want to see this in the form of listing result. So nodal solution X component of displacement. This is load step number 9. So we can save it as file number 9. Okay, close it. Now the last one, read results. Next set or the last set, plot results. Nodal solution X component of displacement. This is the response. Now listing results, nodal solution X component of displacement. This is the last step, right? You can see it, load step number 10, and you can save it as file number 10, right? Done. Now all these results will be useful. That one will show it later on. Now the thing is, we can see the vibration of this beam also. That can be viewed from plot controls, animation, and we can animate deform shape or deform results also. Let us see deform results. And with the default setup, translation along X direction, animate this one. See how it is vibrating. Now by changing the delay, we can make the beam vibrating with a higher frequency. This way the beam will be vibrating, right? Let us close it. You can see the beam in 3D also. For that, plot controls, style, size and shape, display of element should be on. Okay, you can see this is the beam, right? You can see in a better way. This is 3D beam, right? Fine. Now the thing is, our task is to see the displacement of the middle node for the complete duration of time for 10 steps, right? Now the thing is, what we have taken that can be transferred to Excel, and we can show it in a different way. Let us close it, and we can go back to our previous results. Let us take these files. This is step number 1. We're opening this one from Notepad. You can see the 11 defined nodes are there, and within these nodes, the middle node is this one. 6th node is the middle one. We're going to see the displacement of middle node for these 10 different steps. So this is the middle node when time equal to 0, right? So for 0 duration of time, this one was the displacement of the middle node. We can copy this part, and also we can create one file, Excel file you can create. The first one, we can save this as time. Second one is displacement of middle node. We can make this a little bit bigger. This is the displacement of middle node, and the thing is, we started time at 0.01 second and it continued up to 0.1 second, right? So next one will be 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, and finally 0.1. So these are the different time steps we have considered. This is step number 1. So we have considered total 10 steps. For first step, all the nodes were actually having no displacement, so the displacement of this one is 0. You have already copied that. Now the second one we have copied. This is the displacement of the second step. Let us paste it. Similarly, we need to paste the middle node. We need to paste the displacement of the middle node for the different 10 steps, right? We can do it one by one. Now the third one, we can open it, and this is the displacement of the middle node. Copy it, and that can be pasted there. For the third step, we are pasting that one. Now the fourth one, this is the displacement of the middle node. Copy. That can be pasted here. Done. Fifth one, open it. This is the displacement of the middle node. Copy, paste here itself. Sixth one, Open it. This is the displacement of the middle node, because total 11 nodes are there. This is the middle node. Copy this one, paste it here itself. Now the 7th one, open it. This is the displacement of the middle node. Copy and paste it here itself. Done. 8th node, open. This is the displacement. Copy, and that can be pasted here itself. Number 9, open. This is the middle node. Copy, and that can be pasted here. Finally, the last one is 10th one. You can open it from here. The displacement of the middle node, we can copy and paste it here. We have pasted all these things. So these are the displacement of the middle node at different times. These are the different times. At 0.01 second, displacement was 0. At 0.02 second, displacement was 2.02. These are the displacement of the middle node, right? Now what we have to do, we have to plot these things to see the response of the middle node. So what we'll do is, we can insert, plot, and we can select data from here to here. Okay, so this is the plot we can see. Let us make it a little bigger for understanding in a better way. So we started from here. So this is the curve. It is sinusoidal curve. If we continue this curve for more duration of time, we can see that it will be damping in nature. So the amplitude will be decreasing after some time, right? We have plotted those displacement at those specific times, and we could see that the nature is sinusoidal curve and it is damping in nature. So this is all about our today's analysis. This was a very simple transient analysis of a beam, and in this case we applied a step load for a small duration of time, and we have noted the response of the middle node for a particular period of time, right? So with this one, we'll conclude our today's video. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.